Hello, everyone. It's me again, Billy Younger, just here to work some physics problems for you. And this one is not so much a problem as much as it's something to help you understand the difference between velocity and acceleration and what the signs actually mean. We've previously in other courses, and hopefully you've already learned the difference between speed and velocity. What I tell my students is to remember speed, which starts with an S, uh, is a scalar, which also starts with an S. So that's a good reminder. And a scalar is just a number, just a number. It might be a denominate number, which means it might have units. And in this case, the scalar speed does have units. It has units of length divided by time, or it has dimensions of length divided by time. So that might be miles per hour, or meters per second, or inches per fortnight. Okay. Velocity, on the other hand, starts with a V, just like the word vector does. And the difference between velocity and speed generally is that the velocity is a quantity that has some speed associated with it, and that's often the magnitude of the velocity, but it also has a direction. So, for instance, you might say uh, the definition, for instance, of a constant speed is for a given time interval, you cover the same distance each time. So let's say we're going to use the time interval of 1 second, and let's say you're going to cover a distance of 3.85 meters. Then your constant speed is defined to be 3.85 meters per second. And that means every second it's traveling, it will cover exactly 3.85 meters, at least up to that number of decimal places. That's what the definition of constant speed is. Constant velocity has a similar definition, but it has the added conundrum that constant velocity covers the same distance in a given amount of time. So, for instance, if you chose a second, it might be 3.85 meters, but it also has to go in the same direction because of velocity being a vector quantity has a magnitude and direction. Now, if you imagined actually going in a circle, maybe you hit a home run and you run around first base, second base, third base, back to home, and end up basically right back where you started from, then you've completed a complete circle. And the definition of average velocity, for instance, is displacement divided by time. And the displacement is really your initial or your final position minus your initial position, and final position minus initial position gives you zero there. So that gives you a zero magnitude of velocity, but you know you had some speed there. So in that sense, you're not really supposed to call the magnitude of velocity speed because they can be quite different. Okay, so hopefully that's a good enough indicator or reminder of what the difference between speed and velocity are. What I'm going to do now is just take velocity and look at it from different coordinate systems, and then examine it again in terms of acceleration from different coordinate systems, in hopes that you can understand not only the difference between acceleration and velocity, but the difference and dependence on the actual signs and their meanings. So let's start by watching a video. We're going to watch a short video I did in my front yard of a golf cart riding by. Okay. So I'm going to share my screen with you. Okay, so this is the golf cart, and this is the person across the street's driveway. And you can see basically what's going on here is this repeats over and over. A person's riding from outside the screen, crosses this point right here is what I'm using as an indicator, is where the driveway meets the road. And then 1.05 seconds later, they're at this point. I've actually taken the time to slow this video down, time it exactly, and then correct for the slowing it down. And I've discovered that it is, in fact, 1.05 seconds is probably my best estimate of how long it takes for the front wheel of the tire to be there and then the front wheel of the tire to be there. I've also gone out and measured that. That distance is 8.344 meters. So it actually did go a distance of 8.344 meters. And you might think, just everyday life, hey, I'm standing here. Probably the best coordinate system for me to use, and the one that feels most natural, is put the origin right at where the driveway touches the road and make the x-axis horizontal, pointing to the right. And then, of course, the y-axis would intersect it right there where the road hits the driveway, because that's where the origin is. So I have a vertical y-axis right there. And that's perfectly normal. But what I'm going to do is look at not only that aspect, I want to also consider someone maybe sitting in the back of this truck. They would look and just as naturally think that to the our left, which is to their right, is a much better coordinate system for them, and therefore they might put the origin right here with the y-axis here, and then the x-axis that way. So I'm going to attack it from two different ways, and I'm going to make use of a couple different equations. So let me stop sharing a second and show you what equations I'm going to use, and hopefully we can make some sense out of this. So I'm going to turn on my document cam, and what we're going to use in dealing with velocities, we're going to use the formula for average velocity. And the formula for average velocity actually works here because this golf cart really isn't speeding up. It's actually probably going at its top speed and went the same speed the whole time. So I'm going to use the average speed, which is in fact the same thing as the actual speed, the instantaneous speed. And the formula for that would normally be V with a bar over it, but V with a bar over it, in this case, is the same thing as just V instantaneous. And that's given by the final position minus the initial position, x sub 0, over t minus t0. Again, like we almost always do in physics, we assume the initial time is 0. When I go to attack the individual acceleration, we're going to use the average acceleration formula, which in our case, we're going to assume it's a constant acceleration. So I'll just say a is equal to a bar. That means the actual acceleration is the same thing as a constant acceleration. It's not exactly true, but it's okay. So that turns out to be v minus v initial, that's v final minus v initial, over t minus t0, again making that 0. Now the big thing here is in that video we just watched, I told you that they went 8.344 meters in 1.05 seconds. Now I'm going to also, it turns out this vehicle can accelerate to that speed, that top speed, in about 1 second. I'm going to round it to a whole second. So when I do acceleration, I'm going to say it goes from 0 to 7.95 meters per second, which you'll see where that comes from in a second, in 1 second. So I'm going to say it can reach the speed that we're going to determine to be 7.95. It can do that in 1 second. And not only that, the brakes are good enough that it can go from that same speed, 7.95 meters per second, to 0 in 1.00 seconds. And that'll give me a way to calculate the acceleration in the two scenarios. Okay, so notice I've got a speeding up and a slowing down type problem that I'll be using here. And this one I had just two different coordinates. So what we have is that t equals 0 seconds, and this is from my view. So this is my view. This is where we see x pointing to the right. In other words, our positive x-axis is pointing in the direction the person was driving. What we found is that t equals 0.00 seconds, that the velocity, or excuse me, the position x of 0.00 seconds was equal to 0.00 meters. And that's what we call position x0. That's the initial position. So I saw it moving from left to right, and it hit my origin right at when I started my timer. So it had 0 meters at 0 seconds, again, t0 being 0. Then 1.05 seconds later, it was at the other end of the axis, and I actually had that little marker on there when you'll see the coordinate system. I'll show you in a second. So at 1.05 seconds, we actually had a distance of 8.344 meters, and that's x final. So what I'm talking about here is this coordinate system. So I'm going to share my screen again with you. And I am going to share this screen right here. And this is my coordinate system. Notice I did put the origin, which is where the y-axis and the x-axis intersect. I put the origin right where the driveway meets the road. And I did measure the driveway's width to be 8.344 meters. And the x-axis is in the direction the vehicle was going. So you can see, yes, at 0 seconds, it crossed right here. And then at 1.05 seconds, it crossed right here. So that's where I got the data that I was just using. We're going to use the other coordinate system in a second. So right now, let me say my velocity would turn out to be x minus x0. So that's 8.344 meters minus 0.00 meters over 1.05 seconds, which turns out to be positive 7.9 1.5 meters per second, which is about 17.8 miles per hour. Since I know we're used to miles per hour a little bit more, I thought I'd go ahead and tell you that. So this is on the order of 17.8 miles per hour, which we normally just write with mph, and that would be fine as well. So that's miles per hour. And this is my view. So my view has a positive velocity, and that seems to be the result of the actual object moving in the positive x direction, and that is the fact. That's what the, in one-dimensional motion, the velocity, the vector characteristic of velocity is indicated by the sign. In one dimension, you choose one direction being positive, the other direction being negative, and the positive sign is all you really need to indicate the direction. So this one's obviously going to the right, or in my neighborhood, that's about due south. Now, from the neighbor's view, well, we're going to work the same thing. Now, the neighbor's using a slightly different coordinate system, but it's actually a very natural coordinate system for the neighbor to use, and it's this one right here. So for the neighbor, he might have put the origin there, but then that would have been weird because then he'd have the negative x-axis measuring, but that, that's not necessarily a decent one. So let's assume that he did in fact put the origin right here at this end of the driveway where the driveway meets the road, the y-axis being right there, the x-axis pointing to his right, which is our left, and of course he agrees that the width of his driveway is 8.344 meters. So in this scenario, the velocity he ends up getting is given by the same data we had before, but notice t equals 0.00 seconds implies the position of the object being at positive 8.344. So x final is 8.344 meters. And then at t equals 1.05 seconds, he finds that x, and this was, by the way, x0, he finds that the final position is, in fact, at 0 meters. So with this equation, he's now going to say 0.00 meters minus 8.344 meters divided by 1.05 seconds gives me 0 minus 8 gives me a negative 7.95 meters per second. So we see, okay, in this case, in his coordinate system, to the right is positive, and that's our left. And the vehicle definitely went to our right, so he should agree that that's a negative direction, and that's exactly what the sign came up with. So let me show you my calculation. I'll stop sharing. So again, we took t equals 0.00 seconds. That's the instant that they got into this side of the driveway, and that position was 8.344 meters according to his measurement. And then 1.05 seconds later, he had moved from his 8.344 x coordinate to the 0.00 x coordinate. So final minus initial was 0.00 meters minus 8.344 meters. And then the time taken was 1.05 seconds. So we got negative 7.95 meters per second. So you can see there that the sign is really indicating which direction you're going. And it doesn't always have any bearing with what answer someone else in your same class might do, even solving the same problem, because if you drop a ball, someone might see an advantage to pointing the coordinate system down, in which case the y-axis points downward is positive. Or some other person might say, well, the initial velocity was upward, so I called upward positive. And you guys would still get the same physics answers correctly if you did everything like you're supposed to, but your answers would definitely differ because you've used different coordinate systems. And there is no such thing as as the coordinate system, the right coordinate system. Any coordinate system is okay to use. That's sort of one of the laws of physics, or the law of relativity. So we've now got an understanding, if you will, of the velocity versus the speed. The speed would have just been 7.95 meters per second, but because I put a plus in front of it, that tells me, oh, he's drawn a coordinate system, and that vehicle is going in the same direction as his positive axis, one of his positive axes in that coordinate system. And then you look at this one, you see a negative, you say, oh, some other person has drawn a coordinate system in which this vehicle is going in the negative direction, and that's another velocity. Now that we've done that, we want to think about acceleration. Okay, so I mentioned to you before, the definition of constant velocity is traveling the same distance every unit of time. So for concreteness, you should think of a particular unit of time, whether it be an hour, a second, a minute, or whatever is fine. If you think about it as a second, you'd say, okay, well, every second it's going to go the same distance if it has a constant velocity. That's what the 7.95 means. It means if this thing is truly constant velocity and constant speed, then every second it's going to cover 7.95 meters. Now, if it's also constant velocity, it's also going to cover 7.95 meters in a very specific direction that's not changing. In our case, he's headed south. So that's what velocity is, whereas speed is just 7.95 meters per second. Now, acceleration is another beast. So acceleration, it's being a constant, could be defined as for every unit of time, you have the same change in velocity. That's what the definition of constant acceleration is. For a given unit of time, you have a change in velocity that's always the same. So for instance, if you found that an object velocity changed by 1 meter per second in a single second, if it's truly constant velocity, every second its velocity should change by 1 meter per second. So the first second should change by 1 meter per second. The second second should change by another meter per second. So if it started off, say, at 28 meters per second, then after 1 second, it becomes 29. And after 2 seconds, it'd be 30. And after 3 seconds, it'd be 31, so on and so forth. So constant acceleration means the velocity is changing, and it's got to change by the same amount every time. That could mean just changing the size from 9.0 to 10.0. But it could also mean change the size from 9.0 to 10.0 and change the angle from 0 degrees to 15. If it's constant acceleration, that would be another way of thinking about it. So now that we have that sort of major difference between acceleration and velocity, constant velocity is a concept in which an object covers the same distance in a given unit of time. Constant acceleration is a concept in which an object changes the speed by the same amount in every unit of time. So the equation for acceleration we already did. What I'm going to do is I'm going to first take my view, and I'm going to say speeding up. Okay, in my view, and in speeding up, what do I mean by that? I mean that the t equals 0 seconds is going to have my v0 be 0.00 meters per second. And then at t equal 1 second, remember I told you it's kind of neat that these electric motor, or in this case a gas motor golf cart, can actually accelerate quite rapidly. And in fact, we found that it can go to that speed of 7.95 meters per second. It can do that in 1 second. Okay. So what that means is after 1 second, the velocity is going to be, in my frame, it was positive. So it's going to be positive 7.95 meters per second. So the acceleration, which again is really the average acceleration, but we're assuming it's constant, the acceleration should be 7.95 meters per second minus 0.00 meters per second over 1.00 seconds gives me 7.95 meters per second every second. Now that's a pretty fast acceleration. That's, more than 3/4 the acceleration due to gravity, and it came out as positive. So in this coordinate system, where I chose the positive direction to be consistent with the direction the vehicle was going, we found that a positive acceleration meant speeding up. Is that the fact, though? Is that the way acceleration works? Well, what we're going to do now is look at the neighbor's view. So this is the neighbor, and it's speeding up as well. So in this case, t equals 0 seconds. The initial velocity, of course, was again 0 because it's speeding up. That's just something we decided upon. And then after t equals 1.00 seconds, the vehicle will be going the same speed that it did before, and in fact, the same velocity, which we decided was a negative. So the final velocity is negative 7.95 meters per second. So the acceleration in this case would be negative 7.95 meters per second minus 0.00 meters per second over 1.00 seconds. So we're going to get negative 7.95 meters per second per second. So in that case, we actually got, even though it was speeding up, we got a negative acceleration. But that was what it had to be. And what this tells you is that a positive acceleration can mean you're speeding up, but that's in the case where you're going the same direction as the positive direction. In this case, we also found that a negative acceleration can mean you're speeding up, but you're speeding up in the negative direction. So that's what happened here. Speeding up in the negative direction gave us a negative acceleration. So now I'm going to try my coordinate again, but this time, instead of speeding up, I'm going to use it as if it's slowing down. So slowing down. So I'm going down here. I'm going to take some new data. What I have is at t equals 0.00 seconds, my initial velocity is going to be, in my world, it was going to the right, so it's positive 7.95 meters per second. So I'm assuming it's slowing down, so I'm going to start it at the same speed it had, and I'm going to assume after 1 second it's going to be down to 0 because they got good brakes. So now I'm going to say, okay, t equals 1.00 seconds. Then the final velocity would be 0.00 meters per second. And the acceleration formula, in fact, gives us 0.00 meters per second minus positive 7.95 meters per second divided by 1.00 seconds. And lo and behold, I get a negative 7.95 meters per second per second. So here's a case where the vehicle was actually going in the positive direction, hence I had the positive 7.95, but it was slowing down. So in this case, a negative acceleration did in fact mean it was slowing down, but that's because it was slowing down in the positive direction. Now let's do my neighbors slowing down. So the neighbor slowing down at t equals 0.00 seconds. Remember, he said his right is northward, which we consider to be the negative direction. So his initial velocity is going to be negative 7.95 meters per second. 1 second later, his final velocity will be 0.00 meters per second. And again, we are slowing down because we went from a speed to 0 speed. So this is definitely slowing down. The acceleration should, in fact, be 0.00 meters per second minus negative 7.95 meters per second over 1.00 seconds. So in this case, a minus a negative gives us a positive, so I'm going to get a positive 7.95 meters per second every second. So we actually got a positive acceleration for something speeding up, but that was because it was speeding, or excuse me, for something slowing down. We actually got a positive acceleration for something slowing down, but that's because it was slowing down while going in the positive direction. Okay? Excuse me. I messed that statement up again. We got a positive acceleration for something that was slowing down, but the reason why is because it was slowing down while going in the negative direction. So just listen to that last sentence. Don't listen to the previous two. Here it goes again. We got a positive acceleration when something was slowing down, and that's because it was slowing down while going in the negative direction. In other words, for the person across the street, the negative direction was northward. This vehicle was going southward, and that going south and starting at 7.95 meters per second as its speed, it slowed down to 0 while headed again southward in a north positive direction. It came out to an acceleration of positive 7.95 meters per second. So you might want to, make a little table of when the acceleration is positive and when it's negative. And there's actually, a couple different ways. Positive acceleration could mean speeding up, or it could mean slowing down. Positive acceleration means speeding up when you're speeding up in the positive direction. Positive acceleration could mean slowing down when you happen to be going in the negative direction. And then negative acceleration could mean slowing down, but it would have to be doing so in the positive direction, which is the last one we got here. And then negative acceleration could, in fact, mean speeding up, but it'd have to be doing so in the negative direction, which is what we got up there. Any questions on that? I suggest you send me an email, but remember you can get these actual documents and videos and stuff just by emailing me at billy@physicsolutions, that's an L here, .com. And again, I don't type that on my YouTube channel specifically because people will send me spam. So billy@physicsolutions.com. Tell me which the exact title of the video you're interested in, and I can send you either a link to a Google Doc or I'll email you the document as a PDF. I hope that helps. Have a good day.